We are back here in the lecture of Computer Science 455, Software Engineering. Today is the 6th of May and a Wednesday. Like to remind you about the deadlines. Um, you have uh, submitted your revised SRS, and I'm going to review that and give back to you the result of my review. And you have also submitted SQAP and SPMP. It's the first version, and I will revise them. I will give you the review also of these documents, and the revised SQAP and SPMP will be due this Sunday, the 10th of May. Okay. Next up is the software architecture and design, and this document contains mainly UML diagrams, package diagrams, component diagrams, class diagrams, and which uh, represent the architecture of your software. And the architecture is the blueprint of how the different software components will be put together to come up with the software project. And that is an ongoing event for the week of the 11th to 15th, that is next week, where you do a cyclic process between your design and the coding. So coding and design overlaps, and you come up with your finalized architecture and design at the end of this cycle, which I assume uh, would be up to uh, next week, 11 to 15 of May. Now, the delivery and QA testing of your first iteration, this will be an ongoing event between the dates 18 to the 22nd of May. So if your prototype is ready, you tell the QA that you are ready to have the first iteration tested, and the QA team should have that time 18 to the 22nd to actually test and give a verdict of pass or fail of the prototype. I will talk more about how you're going to submit or carry out the process of telling the QA team that you are ready for testing. Okay, but that's the date that we are going to start the the testing, delivery, and testing of the prototypes or first iteration. Okay, all right. Uh, let's continue our discussion of the systems design, decomposing the system. Now, last week we um, talked about a low-level design of the elevator controller, and it is a small project that we can go directly to the class diagram and begin designing a low-level design of the elevator controller. So we started um, with the class diagrams, and we end up with the final class diagram with the pseudocode of the important methods or member functions of the class. So it is an iterative process, and we proceeded to the high-level design. What if the software is complex enough that we cannot determine the class diagrams yet because of the size of the software. So we talk about the the design of a floor plan, and it is a iterative process, and the design keeps changing depending on what is required. Okay, and analysis is a very important part in the design process because you are able to review the design that you have and find out if the design is appropriate. Okay, and so if you remember in the previous problem um, of the field officer and dispatcher emergency report system, we have the use case diagram as shown here of the dispatcher and the field officer, and the use case are uh, reporting emergency, opening incident, and allocating resources in an emergency system. And what we did is we subject this to sequence diagram analysis, and from the analysis we came up with the uh, this high level design, the high level design of the emergency system. So you identified six packages or components of the entire system. So the field officer interface, the dispatcher interface, there should be a map management so we can locate the incident, the incident management, a module that manages the incident, a module that manages the resources, and of course the notification is also part of the system because we have to have communication between the field officer and the dispatcher interface, field officer and the dispatcher through the notification module. Okay, field officer send, dispatcher acknowledge. Okay, so here is the high level design. We don't know yet the details in terms of class diagrams and pseudocode algorithm, so we leave it as components of the system. In UML, these components are represented as packages, and packages can be detailed later on to consist of classes or packages again if it is still very complex, but it is a way of decomposing the system into smaller parts and detailing or refining that component until we are able to identify the class diagram or object diagram that would fulfill that particular, the function of that particular package. Okay. Also in the design, we also came up with another component called the database. There must be a database to support all the information according to what we have found out in the sequence analysis. We need a database to store all of this map management, resource management, and incident management. So a database is a package that was identified after the high-level design of the 6 components or packages that you have come up with. There is a need for a database. But we have two alternate solutions. One is directly accessing the database by the map management, resource management, and incident management. And the other, there is a storage intermediate package that access the database exclusively. And we said that there is advantages and disadvantages of both solutions. The first solution is the would meet performance because it's very quick, very efficient. If the modules access the database, they get immediate reply. But in this second alternative, you have to go through storage package in order to access the database. So the advantage of this design, the second design, is that if I change database in any way, data structures, additional functions, fixing functions, and so on, the other modules need not know to know that. They are immune to the changes made to the database. We only need to change interface to storage. So storage will need to be modified because of the change of the database, but the 3 other modules need not know the change. The interface with the storage remain the same. Okay, so you choose. If it is performance that you are after, that design number 1 is better. But if your non-functional requirements is maintainability, then the second design is better. Okay? All right. So moving on. Oh, by the way, UML diagrams have changed through the years, and sometimes this high-level design is depicted in this manner. It is a box with this weird-looking symbol on its upper right-hand corner. Okay, so sometimes you will see this in our book, but I would prefer the use of packages because it is very well understood that packages means a group of packages or a group of classes inside the package that needs to be refined, or the package needs to be refined to what is inside this package. So it is very nicely mapped onto hierarchical decomposition of packages. You begin with an upper level, high level design of packages, and then you detail what is inside the package with classes. If it is, you have enough information to determine the class diagram, and if not, then you define what is inside the package by another set of packages, and you go on, so forth and so on, to go through this decomposition process until you arrive at a package where you can define what is inside the package in class diagram. So very nice tool to decompose, okay? Decompose into simpler and understandable object, okay? So here is what I mean when I said I can define what is inside the package with class diagram. So right here, you have several classes representing the decision subsystem. So the package decision system consists of 1, 2, 3, 4, 5, 6, 7 classes. And this is how they interact or association. So the subtask is a superclass with action item and task are, are subclasses of the subtask. There is a class called criterion, assesses the option. There is a decision class, um, and the interaction resolved by in the design problem, and so on. Okay, and so in this decomposition process, we apply the two criteria for decomposing this or analyzing what is inside the package. It must have two properties. Number one, cohesion, and number two, coupling. Okay? Now, cohesion is defined as the strength of the relation among objects or among classes in the class or object diagram uh, with the common task they are doing. So you ask yourself in this decomposition of the decision subsystem package, are all of these classes related in what they do? So are they fulfilling a common function? Or are they involved in a function that all of them actually collaborate to perform? Now notice here that this is a um, um, uh, inheritance diagram consisting of subtasks, action item, and task. And that looks to me as a group of classes that are not related to the four others: criteria, option, decision, and design problem. And look at this, there is only one interaction or relationship between these two groups of classes called implemented by. The decision is implemented by. That's the only interaction of this um, group of classes, which is actually a class subclass relation. So it is very natural that I isolate these groups of classes, subtask, action item, and task separate from these four other classes: design problem, decision, option, and criterion. So we come up with two uh, two packages inside that big package of decision subsystem. Inside the decision subsystem are two uh, uh, packages. One is rational subsystem consisting of the four classes: criterion, option, decision, and design problem. We call that rational subsystem. And the other package, excuse me, the planning subsystem, which consists of the subtask, action item, and task. So this is where you apply cohesion, where all of these classes are related to each other in a parent children relation or class superclass relation, and these others are helping each other to perform another function called rational subsystem. So here in the um, decision subsystem, when you have identified the classes that you think would represent this subsystem, you apply the question of cohesion. Are these can all of these set of classes still be um, grouped into um, other packages? And that's the answer. We can decompose those classes into two subclasses, two packages, and they interact with the single association called implemented by. Okay. Now, the other criterion of a good design is coupling. Okay. How much information does this class relate to the criterion? Or better still, let me look. Let's look at the previous design of the uh, of this information here, of this design problem here. Coupling is the information that the map management, resource management, and incident management knows about database. Since they apply it or they um, access database directly, their coupling is very high. Okay, so that means if I change database, make some changes in the database, the information uh, that the map management, resource management, and incident management will be the cause of the other modules changing their modules as well, the packages as well, because the amount of information that they know about database is high. That's called high coupling, okay, which is bad because a change in database will cause a change also in the other modules or packages that access it. Whereas here in this design here, the information that the resource management, map management, incident management about database, zero. They don't know anything about the information or the data structure that is used in the database. Okay, you will of course know about storage. You have information about storage, but the coupling between database and incident management is almost nil. Okay, you don't know anything about it. Okay, so here in the design of high-level design or even low-level design, you must limit the information of one module or one class over another module or another class between them, because changes in one of them will cause changes in the other uh, parts of it. So what you're aiming for in a design is uh, to have uh, high cohesion That means the relationship between each of the classes or each of the package in or classes inside the package must be very strong. They are related to each other, they perform or they support the same function, then they have high cohesion. And the information that you pass between this package here, rational subsystem, information that you pass to the planning subsystem should be at a minimum. You should not have high coupling. You should have low coupling. That means the least amount of information is a better design. No information is the best. But of course, we cannot avoid no information at all. So we go for low coupling. So remember that in your process of decomposing a system, you go after high cohesion and low coupling. Okay? All right. Another architecture style that we can apply is what we have done previously, and this is a decomposition of a single subsystem into its components. So you see here in layer 1, this is the high-level design of a subsystem, and you decompose that subsystem into subsystem 2, B, C, and D. If you are not, if you still couldn't identify the detail of the B subsystem, you decompose it again into subsystems called E and F. And the same thing with the other subsystem. Now, if you come to a point where you identify the C subsystem to be well understood, then you can come up with a class diagram. Okay, so the class diagram is the last step in the decomposition process. So the class, you can define the class as consisting of a set of member variables and a set of member functions or methods inside those classes. So a very powerful tool in computer science called divide and conquer. We always do divide and conquer in a complex system. We always decompose it into sub-problems or subsystems and keep on applying the decomposition to the rest of the other subsystem until we arrive at a decomposed package that you can define in terms of classes or objects. So that is going to be your method. Okay, a very useful architecture technique on decomposing a system into subsystems. Okay, so you will find this probably you will use this very often in your design. Okay, another powerful design architecture is the layered architecture. Okay, so the layered architecture, if you have taken CSE 430, Data Communication and Networks, this is the ISO OSI data communication model. Okay, so the whole networking data communication is divided into different parts of the datacom. Okay, the highest level of the data communication is the application, like the database of the bank, to the lowest level, which is the electrical signals that are passed between two nodes, the physical layer. And that is represented by the bit that is um, transferred between one node to another node. Okay? So the physical layer is concerned only with the electrical uh, data that pass between two nodes. Okay? So pulse code modulation is one um, uh, technique in passing data between two nodes, and they are concerned only with the electrical level of the data. And then you put them together in a much um, larger unit called a frame, and the frame has a bunch of data that is lumped together in a frame, and then uh, the packet contains the destination. It has its source address and the destination address. So the networking um, layer is concerned with how to route your packet from one node to another. Say a bank here in San Bernardino would like to transfer money to a bank in New York. Okay, so there must be a network that this packet will have to travel from San Bernardino to New York, and that's the network layer. So that package is concerned with routing the packet from the source to the destination. Uh, the transport layer is concerned with the type of communication that you are using. Okay, and so transport is concerned with the messages that you send. So a, a particular, let's say, bank transfer may consist of several packets together traveling to the network, and then um, actually assembled in the destination. And the transport will try to hide whether this is a cable medium or a satellite communication or internet uh, uh, communication that you are using. That hides that information from the rest of the uh, layer here. And so the transport handles the kind of network medium that you are using. Okay. The session establishes the connection. Okay. You cannot just send packets and messages without establishing a connection between the two banks. Okay, so there is a protocol. I want to connect to you, and New York will tell somebody, yes, you may, and then you establish the connection, but information are exchanged for authentication and for login. The presentation layer is concerned with um, the readability of the message. And one example of that is encryption of the message. The bank transfer will contain important information about the bank account and other information about the client who is using the transfer. So we must present it in a before sending it, we must encrypt it, and when it is received on the other end, it must decrypt it. So that is presented to the application, and the application is the database of account. So your account is increased if it is a deposit, or if it is a payment, then your bank account is decreased, or it's credited, okay, and debited. Those are the uh, action done on the account. So you see here that instead of a hierarchical decomposition of dividing, we still divide the problem into its parts, but we separate the different concerns of the system from each other. So the physical layer is just concerned with electrical signals being exchanged between two nodes. Data link is forming organization of the data into frames. So instead of bits, you have bunch of bits together and put into a frame. And then the networking handles the routing of the packet through the network. Transport handles the kind of communication you are using, satellite, cable, internet, and so on and so forth. Session establish your authenticity. This is the authentication part of the data communication to see if you are a trustworthy client. Presentation, one of the presentation um, application is the encryption decryption of data, and of course the application itself, like a database that needs to be accessed and read. So this kind of architecture separates each concern in each package. So inside this package are um, low-level design decisions, which could be classes or objects that we can uh, uh, actually identify. Okay, so layered architecture is used very often in many applications. Okay, and the famous TCP/IP, which is the Internet Protocol data communication, consists of three layers of the OSI layer. So TCP/IP is actually concerned with data link, network, and transport layer. Okay, and the upper layers, session, presentation, and application, is handled by Corba. Corba is a conventional organization that um, creates standard for establishing session and for the presentation connected to each other. And the physical layer is the actual physical layer of the transmission medium that you're using, either uh, internet, Ethernet, or wire itself. Okay. All right. Of course, the advantage of the TCP/IP over the OSI is that in a layered architecture like this, you will have um, efficiency or performance issues, because there are 7 layers of uh, the architecture before the application receives the request. Okay, whereas here we are only dealing with 3 layers: the Ethernet, the TCP/IP layer, and the Corba layer, which defines how are these session and presentation layer are defined. So they have a conventional standard how to define this session and presentation together. So instead of 7 layers, we have 3 layers here in this architecture, and so it is much faster than the ISO OSI layered architecture. Okay, and the layered architecture has been used in many kind of application today, and here is uh, an example of that. X11 is the low-level drawing facility that is used by your computer, and the AWT is a low-level interface provided by Java. So the application doesn't need to know the low-level X11 implementation of user interface. So you're designing user interface. This is what you will deal with, the AWT. Swing is a library that provides a large number of sophisticated user interface objects. And the application access that. So if the application wants to build a user interface, instead of dealing with the X11 low level, you deal with the Swing library. The Swing library will access the AWT, which is a low-level interface um, uh, provided by Java, and AWT actually access the X11. So the application doesn't need to program the interface using X11. They will deal with Swing library, which is an API that consists of callable functions that you don't need to define yourself. Now here is an option to access the application directly to the AWT. If you don't want to use the Swing, you can bypass it. Okay, so this becomes a very good way of building user interface here. Okay, here is another architecture style called the repository architecture. So you have a subsystem and you have a repository, and you guys are working with repository. Okay, Bitbucket, um, uh, GitHub, and many other repository that you have used. So it provides um, um, call routine like create the data, set the data, get data, and search data. So the repository uh, actually keeps everything that you need and provides you with interface call to the repository. So very um, powerful architecture if you are building a repository of data where you handle all this information via this particular function call. Okay, so you don't have to implement a repository, you actually call it. Okay, compiler is a specific example. It's an example of a uh, of this repository architecture style. So if you're building a compiler, you have in the compiler package all these modules or packages that are inside the compiler. So it provides information or it provides function for the compiler writer to access the lexical analyzer, the syntactic analyzer, the semantic analyzer, the optimizer, and the code generator. For those of you who took compilers, you recognize that these five are the five basic components of a compiler. And the information about everything, your data, access is a repository. So the repository contains the two important um, information or data that you need in compiling. You need to access the parse tree and the symbol table. So the application, which is the compiler, all of them access the repository. And you need to access the parse tree as it is being generated and the symbol table to store all the symbols you have read in your in your compiler. And there are supporting packages called the source level debugger and the syntactic editor. Okay? So you see it there. And here is very popular architecture style that we will be using, and it's used almost everywhere. It's the MVC, the Model View Controller Architecture. So it consists of three modules: the controller, the model, and the view. Okay? So the user interacts with the controller, so inputs data from the controller. Controller communicates that with the model, and the model contains data structures that is relating to the information that you are accessing. The model notifies the view, which is what you see on your screen, and so if the controller is accessing, for instance, a website of a company, it will see that information in the view. And the advantage of the MVC is that I can change the view component without touching the other components, the controller and the model. So the model contains the data structure. You can change the user interface without affecting the controller and the model. Okay, and you can change the controller, the way the user interacts with the controller without affecting the model and the view. Let me show you a website. Let me do this. Of the model view controller. Okay, so the model view controller is defined in Wikipedia as a design pattern, software design pattern. It is used for developing user interfaces, which divides the program logic into three interconnected elements. And this is the diagram for that. You have the controller, the user, inputs requests in the controller. Controller manipulates the model, the data, and the model updates the view, and the user sees the change in the view. So the web site is divided into three big components: the controller, which handles input from the user, which is the user interface; the data that you manipulate, or database, is the data structure that you use; and then the the view, what you see on the screen is change, and the user sees that particular change. So it's the standard of writing web um, application, and they are supported. It use um, MVC. These languages provides MVC, JavaScript, Python, Ruby, PHP, Java, C Sharp, and Swift all have MVC frameworks. Okay, but there is um, there is uh, an open source that supports MVC, and this is Laravel. So Laravel is a free open source PHP web framework created by this person, Taylor Otwell, intended for the development of web application following the MVC architecture design pattern. Okay, and we use Laravel in Babelin. Okay? Babelin use Laravel, and any of your application that requires a website, um, uh, this is um, the system that we recommend that you use. Okay, Laravel. Okay, it is PHP um, um, supported by PHP language. Okay, so continuing on, uh, continuing on to the rest of that chapter, let's go to the rest of that chapter 6.2. Okay, so we talk about let me get there. Okay, so we talk about MVC, and you have a look at the Laravel API that we have in the on the open source. Another architectural style is the client server architectural style. So you have a client, and the client requires a service from a server. So client server architecture, and the client, the server contains several services that it provides the client. The example we have is the different browsers that use the server provided for the different browsers that we have. So for the Netscape browser and the Linux web browser, access this web server for that kind of browser, and the Explorer as well. While the web server at CMU provides servers to the Linux web browser and the Mosaic web browser. So depending on what is the need of the client, the server can provide that service, and that's a good architectural style that you may have. Okay. Another one is the peer-to-peer architecture style, and everybody is a peer. It means they can provide service or they can ask service to a peer um, entity. Here is an application of two database users. One is for application 1 and the other is for application 2. So here is the database itself, and number 1 wants to update the database, and the database notifies the application number 2 for the change in the database. So peer-to-peer is also can be used for such an application. Okay, and there are others. The layered approach are limited to 3 tier architectural style, and we have seen systems like this: the 3-tier system, the 4-tier system. And for the 3-tier system, the the packages are divided into 3 tier: the storage itself, the application logic, and the interface. So that is going to be the 3-tier system, where the lowest level is the storage, the application logic is the middle tier, and the interface is at the highest layer. Okay. There is also the 4th tier, as I mentioned a while ago. So storage, application, and there is an additional one, the presentation server. So here you can look at this 4-tier architecture style. The storage is where you present your query. Then the application logic is the connection to the storage. The presentation server presents the form, and the web browser is the presentation layer. Okay, so 3-tier or 4-tier system. They are some type of a layered architecture as well. Okay, and the last one here is the pipe and filter architectural style. So the pipe is some transformation that you do to the data before it can be processed. So the filter has multiple inputs and multiple outputs. And the pipe, when it receives an information, let us say one of the output is given to the pipe, and the pipe outputs it in after processing it and given to the filter. So the filter filters the different inputs and outputs that is received, and the pipe for a particular transformation outputs a transformation in terms of input and output 1. That's one of the different inputs and output. Okay, so that's the lecture for today. So we'll continue from there, and we'll proceed to the next chapter in the book, which is system design, addressing design goals. And so you have an idea about high-level design. High-level design is consisting of packages, and you keep decomposing the high-level design into a lower level design. Uh, but if you are unable to determine the class diagram at a specific level, you still represent it as a package diagram or high level design. And you keep decomposing it until you come up with the class diagram that you can understand a package that you are able to determine the class diagram. Okay? At that point, when you have determined the class diagram, that is the start of the low level design. And another lower level design is the detailed design. And the detailed design is the pseudocode of important methods or functions in your class. And this is for um, making sure that the logic of your method is correct. And you can start testing, analyzing your pseudocode uh, using informal techniques of tracing and uh, trying to simulate what the algorithm is doing, and then checking if the output is determined logically. You want to do that because you don't want to um, fix source code. uh, Fixing source code is, according to some studies, is 10 to 100 times more difficult than to fix pseudocode. Okay, so that's it for now, and be safe and healthy. I'll see you. Bye bye.